Okay, shall I start?
Please.
Yes, all good. So first to start with, it is a introduction for radiation physics and particle therapy. We know particle therapy is the most advanced therapy we use to treat cancer nowadays. Yeah. And for us to understand what are the difference between particle therapy and conventional therapy, we also need to have a background and idea of why and how both works. Now, why this? Why it's not changing the slide? Okay, slide change. So yeah, we will start with the basics, quickly going through the basic from 1 to 3. Then from 4 to 8, we will be more focused to understand the physics we use in our particle therapies. And if you see me talking a lot about some kind of topic, tell me to move next because this is physics and I like physics. I can spend 1 hour talking about each, point. So if you think I am talking too much, just tell me, let's go to next.
Let's go.
Okay. Okay, so next. Oh, there's too much next. Okay, source and type of radiation. Radiation can come from nature. Also, it can be made by a human. We can find it in the sun, in the cosmic rays. And human, we can make it in industry. But what important for me now to start with is the radiation can be distinguished into two. One, we say ionizing radiation. Second, non-ionizing radiation. We are interested in ionizing radiation. And all radiation has types. We all know this, I believe. Alpha, beta, gamma ray, neutrino, and the different penetrating capability for each type. It's because of the mass and charge of each particles. Conventional radiotherapy, they use what we call the photons. I believe everyone here knows photon. And when photon interact with matters, it has three possibilities. Either it will be transfer, or it will be totally absorbed, or it will scatter. Now, why I'm bringing this? Because the way photon interact with matter is totally different than the way charged particle interact with matter. The reason, because photon is uncharged, has no charge. Particles, we have charge. And when photon interact with matter, it go through all those type of interactions. We call them it's called like the photoelectric effect and the Compton scattering and the regular scattering and the pair productions. Every type of interaction happen in a certain kind of energy. For example, when the low energy of this when photon's energy is very low, the probability of photoelectric effect happening is dominating. When the photon energy in intermediate level, the probability for Compton scattering to happen is higher and more dominant. When the photon energy is very high, pair production is going to happen. And then the things we should consider in our photon therapies is what we call attenuation coefficients, which is this equation I think you are all familiar with. And in this equations, we have really pay attention to the linear coefficient attenuation and the mass attenuation coefficients, linear attenuation coefficients and the mass attenuation coefficient, which make me understand how photon interact. with materia. And then the X-ray, the photon is traveling along the path, does not interact too much with matter, so it is easy for the photons to penetrate. However, in its path, when those things happens, will produce charged particles, will produce electrons. Now, these electrons, the charged particle, can be used to treat tissues or cancer or toxic cells. So, whereas it is not, it's frequently interacting with matter, whereas in charged particle like carbon and protons, since the particles start interacting with matter, it start lose energy. It's continuously interact with every with the whole path, keep interacting until it lose all its matter. So quickly mentioning that photoelectric effect is the process when the photon interact with an air shell of the atoms, and then the electrons, the atoms there, the anneal shells, completely absorbed by the energy of this photon. The electron will be ejected, and then energy, kinetic energy of this photoelectron will be equivalent to the binding energy, then X-ray will appear. And pair production also quickly, it's that when the photon is interacting with the nuclei itself with high energy, so what will happen, some positron and electron will annihilate and yeah, they will appear with energies of 5.11 MeV each one. So for this pair production to happen, the photon must has energy higher than 1.022 MeV. Compton scattering, which we have it a lot in particle therapies, it is when the photon collide with the bound electron. So the photon is not absorbed completely, not in the nucleus, not in the electron. However, because of the collision happening, it will change direction. We call it scatter. So it will scatter and will lose some energy, whereas the other electron will gain some energy, enough to be ejected from the shell, from the orbit or the inner shell. And then the last one, it is not losing any type of energy because it's interacting with the whole atom as a whole, and it doesn't just make the atom shake a little bit, and the photon will slightly change direction or scatters. Now, what is more important for us is the charged particle interaction with matter. It is not like photons because they are continuously interacting through what we call Coulomb forces and nuclear interactions. Those are the most important two things for us in the particle therapy. Why? Because when the way a charged particle loses energy is through excitation or ionization when they interact with this matter. Now, excitation is that when the collide happen between the two charged particles, energy will transfer to the electrons. Now, the atom will be excited when the electrons from the lower shell has gained enough energy to jump to the upper shell, and when this happens, we call this the atoms excited now. And then after this excitation, the atom needs to relax, so it will release energy, and this energy is released, it will be either heat or some kind of radiation. And ionization, before I go to ionization, I should mention that this excitation happens more in the path of our Bragg peak, in the beginning of our Bragg peak. Ionization is that when the electron is removed from the atom and create hole. This hole, because the electron here was negatively charged. When I take this hole, when the electron is removed, the hole become positively charged. So it is, we call it ionized. This area should be negative, but the negative has removed. So now it is positive charge.
The whole, sorry, how is that whole appear?
Now, how that we we send an electron, for example, our charged particles, electron. So the electron is negatively charged. So when it comes to this, near this shell, there is a negative charge here. Then repel will happen. Instead of attraction, repel will happen. Now this repel, if the energy is enough to kick this, remove these electrons, create a hole, vacancy. This vacancy is the ion, the positive charge. We call it the ions. And when we, because we have this ions and we ejected this electron, we call it this, our charged particle is coming, the electron ejected here because of this repel, it's called delta electrons or secondary electrons. The multiple Coulomb scattering, which mean the charged particle is moving around, but it's not colliding. Instead, it's scattering between the nuclei of an atoms and gradually start to slowing down, because when it flows some energy while scattering. Then last one is the nuclear interaction, which is responsible about, if you remember our Bragg peak, the fragmentation tail. Last one is the nuclear interaction, which occurs less than the Coulomb force interactions. So when we're talking about Coulomb force interactions, it's mean we're talking about excitation and ionization together. The nuclear interaction produce the nuclear fragment. We will talk about in the upcoming slide more details. And yes, those are the way charged particles interact with metals, and those are illustrations of how when a charged particle move along the path with multiple Coulomb scattering, they are not actually interacting with the nuclei, so there is no excitation, or there is no ionization. Sometimes it is just slowing down. For excitation and ionization to happen, particles should collide with the atoms, or with the electrons around the nucleus or with the nucleus itself. In case when the nuclear interaction happen, when the particle collide with the nucleus, our charged particles, for example carbons, is very heavy. It produce secondary particles. When they collide, those energies produce protons, neutrons, deuterons, alpha particle, scattered protons. They all have some kind of energies, and they will be produced because of this particle interaction with the nucleus. Now, this is the equation of Coulomb force. If you know it, I think it's easy. Attraction and repel between two charged particles. Also, the size of the mass matters. And here, to show that I like to look at it by this way: is 3 different length. When the length of this parameter is equal to the radius of the circle from the nucleus, then I will have either excitation or ionization. When the particle moving, the distance between the nucleus and the movement of the particle is equal to the radius of this atoms, I will either have excitation or ionization. When the radius, when the particle distance very far away from the radius, double the radius, I will have multiple Coulomb scattering. And then when the length is less than the radius, I will have the nuclear interaction, most likely, for a charged particle. Now, the way I am saying it is not 100% correct. It is just the way I look at it for me to understand. And here, as you can see, they call it hard collision. When the B is equal to A, this is A, this is the radius, B, this is hard collision. When B is way less than A, it will be soft collision. And then when B is slightly larger than A, is gonna be soft collision. When B is less than A, it's gonna be radiation collision. And also, it's very important to consider not only the charge and the distance, the mass of the particle itself. Different mass has different things. Now, the way for a charged particle to interact with the atom is not as easy as it sounds, because there are all those way when the charge interact with the nucleus, and this is when the charge interact with the electrons around the nucleus. There are many different scenarios and probability for things to happen, but in general, we can say that excitation and ionization are more likely to happen than the radiation, the nuclear interaction. So the hard collision and the soft collisions are more likely to happen than the radiation collision. And again, in photons or neutrons, there are no collisions happening directly. They travel until something happens, either absorptions or scattering, and they lose some kind of energy. This energy inside the atoms, they interact, they produce electrons, and the electrons cause the damage for our tumor. For charged particles, since the charge appears, collision is happening. In the beginning, it is slowing down, so it is multiple Coulomb scattering, low collisions, soft collisions, until it gets harder and harder collisions, but the probability of hard collision is happening more. All the way along the path until it loses all its energy and drops. At the same time, when this is happening, there is also a nuclear interaction happening. And I think this is, we mentioned before, and we talk about it, excitation and ionization of the electrons in the atom absorb energy and move to higher energy state atoms is excited. If an electron in an atom absorbed enough energy to leave the atom completely, the atom is said to be ionized. Spelling mistake here, human aside. By gaining or losing electron, it becomes charged particle. We call it an ion. And that's what we use to treat here in Gul Mahavi Ion Medical Centers. We have ions, and because it's from carbon, carbon is heavy. So we got heavy ion. The ionization energy is the minimum energy needed to remove the electron from the atom completely. So it has to be higher than the binding energy that connects the atoms together. Now we understand how the particles is going to lose the energy, but how the particle will stop is related to what we call the stopping power. Now the stopping power is equal to the collision stopping power plus the radiative stopping power. Now, in our collision stopping power, we have the hard collisions and we have the soft collision. And then we have the radiation collision. So the total stopping power, it has to be the hard collisions plus the soft collision, that's the stopping collision power, plus the radiative collision with this radiation collision power. Now, when a particle is moving inside, and materia, things matter. What is the Z number of this materia? It means the atomic number of this materia is responsible of causing more or less collision. Some materia can cause more hard collision, less soft collision. Other materia is the opposite, can cause more soft collision. The amount of collision is happening will determine how much energy were absorbed in this type of materia with this thickness. Also, thickness matter. Size of material, very important. So what I'm trying to say here is that stopping power is telling me that some kind of some kind of materia with this kind of Z number, atomic number, has the probability to prevent or absorb charge or absorb this amount of charged particle in this distance. Some material they can do it in for example, 1 centimeter is enough to absorb 4 electrons. Other materials you need 5 centimeters to absorb 4 electrons. Now, if I put 2 of the same material, things differently will happen. If I put 2 different material, story is different. Now, in my case, I put particles is coming through the skin. Then after the skin is gonna go through the bone. Then after the bone is gonna go through the blood. So the scattering is different, the absorption is different. Each one of them has different way of dealing with the. However, each one of them, their densities is different, but has certain kind of stopping capabilities. That's the stopping power. The capability of this material to stop how much amount of whatever type of radiation or ionization I'm choosing. So stopping power equations in general, it is the N here is the number of particle interaction per volumes, how many particles inside the volume. T here is the average energy transferred in interactions. So the average energy has transferred in this interaction, for example. How many energies being transferred here? And sigma is the cross sections or the cross section of interaction, probability of interaction, how many times it will interact. And this I here everywhere, it is the number of excitation or ionization or the scattering.
How we determine the value of I?
How do we determine the value of I? Yeah, how many number?
Okay, I understand.
So how many particles is coming? So you understand? Okay. Then I move next.
Can I back to the previous one slide? So the figure on the right corner,
This one.
the down corner, yeah, this one. Can stopping power explain this figure?
This is a stopping power.
Right?
This is.
Yeah, this is stopping power, and this.
So we have this figure
Mhm.
because we have stopping power.
Yeah.
If we don't have stopping power, we will have something like this.
Yeah.
But we have stopping power. You see the charged particle are slowing down until they stop. Then rapidly go down. Now what caused this? What make them stop here? Is this what make me have all this path is the stopping power. Because when they first interact, let's say for example they enter air. I shoot, there is air. In air, the stopping power, the Z material, the atomic number of the oxygen of the air is very low, so the stopping power is very low, so many particles will go through. However, due to multiple Coulomb scattering, some will slow down. And then I will have some fragmentation here coming soon. But then slowly going to the skin, slowing more down, then slowly going to the bone, slowing more. Thickness of the bone make the stopping power higher. We lose more energy. Deposit more energy until it reach here. Does it make sense?
Why X-ray don't pass the
Because
stopping power?
because X-ray is a photons,
Yeah.
and photons are not charged. So in photons interaction, there is no excitation and ionization. There is only photoelectric effect, Compton scattering, and those Bayer production. This type of interaction will lead to the production of charged particle like electrons. Then electrons will experience similar things to those because electrons are charged. But electron energy is not strong enough to make Bragg peak. Electron energy will be absorbed very quickly. I move next.
Yeah, please.
So again, let's continue. Stopping power. It depends on the number of particles interacting in the medium. It depends on the energy transfer interactions and the probability of interaction. Now, this is the equation we use to present the stopping power in our field. And this is a very amazing, beautiful equation. Take too long. I try to show you how before when I prepared my slide, I try to show how can we reach this equation. And for me, I love it. I like it, but I think it is when I did it, I think it will be too much, and because we came from different background, one is biology, one is doctors, one physicist. I don't think it's worth to share how we drive it. However, it is important to know it. So what is happening, and this is our stopping power. Basically, we are saying that the higher number of charged particle lead to higher stopping power. The more charged particle I have, the more the stopping power will be. And the other one, the slower the velocity of the particle lead to higher stopping power. This is the velocity of the particle. This one. This one. So the slower the velocity, the higher is the stopping power. Does that make sense? And the last one, the denser material lead to higher stopping power. The density of material, it depends on the atomic number as well, but the denser it is, the more probability to stop particles. So the higher is the stopping power.
Okay, maybe it depends on the charged particles and its velocity and density of materials.
Now, not the only, those are the most important things. There are many things, but for us, the most important things in this equation to understand is that density of material, the velocity of a particle, the number of the particles. If we can know those are enough information to understand the stopping power. And we now by now we understand that as charged particles moving is slowing down and the stopping power increase. Now this increase produce what we call the Bragg peak. So we have 1 particle, 2 particle, 3 particle, 4 particle, 5 particle, all particles together. Each one of them will do like this. And it depends on the number of particles, the atomic number, the Z material, the density of the Z material, and the speed of this particle. Sometimes it will stop here, sometimes it will stop here, sometimes it will travel further. But this for us is not uniform. Does not make any sense. This is just particles stopping everywhere somewhere. We cannot benefit from this. So we have this amazing idea of taking the superposition of those Bragg peaks for each particle and spread it out so I can have a uniform energy in the end of Bragg peaks, which allow me to use and treat tumor. So I want to say this one more time again, more clearly, more slowly. So particles, excitation, ionization, multiple column scattering, and nuclear interaction is happening while they're traveling along the path. Now, when the nuclear interaction is happening, it's very low, but it is happening. This interaction produce fragments, secondary particles, produce neutrino, protons, neutrons, uh, whatever secondary particles. Yeah? So it is happening. When the excitation and ionization is happening, the charged particle is slowing down, which means stopping power getting higher. Stopping power getting higher along the path until the charged particle stop, lose all its energy, rapidly fell down. When it's rapidly fell down, all the secondary particles with the nuclear interaction here start to produce the energy, the LET, linear energy transfer, instead of the particle itself, and they make the fragmentation tail because of the nuclear interaction. We will talk about different. Now we are interested in the energy in the peak here. This is very good for us to treat, but by itself is not enough. So we take a superposition of each particles with this energy. We use, for example, what do you use?
Superposition method is the formula.
Yeah, but what do you use to make the width of a Bragg?
Optimization process, like summation all brackets value.
No. The filter you use, the ridge modulator. Okay, so we use the ridge modulator filter to spread out the particles and decide the width of the Bragg peak. Now when we do
our target volume is different thickness, so like round shape. So from here to here we want to treat. So it's not 1 millimeter, like it's 10 millimeter, here 20 millimeter, 10 millimeter. So we layer by layer we set these things. This will be the size, this will be width, so that we can perfectly treat our cancer.
yes, so as you said, we have our target, which is the tumor over here. We want to treat from here to here. So we need to set up the width of our Bragg peak to cover the tumor size and send the energy. Now, magic happen that our physical dose and our RPE are also depending on this stopping power. So we have clinical dose. This is the dose we are treating with. And then we had our physical dose. This one, physical dose. Now this physical dose is the dose deposited because of the uniformity of a Bragg peak.
Sorry.
This physical dose is the dose deposited on the patients or on the cancer or on the organs or on the target from the Bragg peak. From the Bragg peak. Spread out Bragg peak. So this is the charged particle moving and spreading out. We spread it out with energy, different depth, different travels, drop. Now when the charged particles moving, this is the amount of dose depositing. This is the energy is losing. Deposit this here, it was a little, then slightly increase. Now here it is not uniform. It is changing, decreasing. Why? Because here it is a sum up of many. It is not one. It is a sum up of many. Superposition of sharp Bragg peak. So everyone will deposit some, then lose, some, then lose, some, then lose, some, then. Now, when this is happening,
I forgot the physical dose formula.
when this is happening, RBE, RBE, radiobiological efficiency, does, effectiveness does, having the same relationship like the physical does. We start again. This is the charged particle traveling. This is the spread out Bragg peak. Yeah, we understand how the physical does behave. RBE will do the same. We'll start with the same, we'll increase a little bit, then it reaches its maximum, then drop. Because the RBE, it is also will be related to each sharp Bragg peak. For me to have this clinical dose uniform, like this line, to make him this line, I need to make sure that the physical dose and biological dose are following the same path, uniform too. Does that make sense? I cannot have this one uniform if those are uniform. Those has to be not uniform. To make the clinical dose or the biological dose uniform, physical dose and RBE should not be uniform. If I want to make the physical dose uniform, then I will struggle with the making the physical, making the clinical dose or the biological dose, weighted biological dose, uniform. Does that make sense? I move next or I keep going here?
Why the physical dose decrease a little?
Why does
deep tissue?
Why the physical dose decrease here? You mean this point?
For the deep. the deeper in the tissue. Why it decreased?
Why decreased here?
Yeah, the dose. Why so
Because
Actually, when we say the physical dose or IV dose, what we understand, through the Bragg-Peak or spread on Bragg-Peak, we understand the tumor volume is treating that layer. But others, we also consider those things, clinical dose, there's many kind of dose, LET. So each parameters how what actually physicists understand when they say what is the effectiveness or how they determine is this good. I understand. I want to understand that those things.
okay, but first let me say to Dr.
I think
Lewis.
I asked you this question before. I forgot the question.
Yeah,
The answer.
but it's okay. We can remember.
Okay.
We can. So, why the physical dose drop inside the tissue?
Yeah, and increase a little and decrease and.
Now the increase a little here. It's because this is not. This is not one Bragg-Peak.
Yeah, of course.
This is superposition of too many Bragg-Peak.
So
this increase a little
line
is this. This
okay.
the little one.
Yeah.
Yeah.
The little peak is that little one.
The sum up of the three. Let's say, for example, sum up of the three first little peak.
Okay.
For example, they're not. This is not the right number. I'm just giving an example. Yeah. So the sum up of the three little peak will make me have the beginning here. This one. Because, but then when they get larger, each one by itself. So each one will deposit its energy by itself. The more that you go, the less dose they will deposit. Because the more you go, the stopping power is higher. Exactly. Until you reach the moment where the stopping power has the highest.
Highest. Okay.
So the particles already stopped.
Yeah.
No more energy. We cannot say no more energy because there's a little energy deposited here.
Yeah.
But the main dose is no longer deposited from the particle. The dose is now happening from the secondary particles.
So the higher the stopping power appear, it is the lower dose.
No, the higher the stopping power appear, the lower the dose.
Right? Just like the graph show. No?
Yes, you are right. But because the dose.
Can we see like in this way? Can we see it?
Because the higher the stopping power, the lower the dose. I think, yeah, you are right. But the relationship for the stopping power is not to determine the dose. Is to find out the energy. And then this energy is responsible of depositing this amount of dose. You understand? So for me to understand stopping power, I am not trying to understand how the biological dose behave or physical dose behave or clinical dose behave. No, when I'm trying to understand stopping power, I want to understand the energy that I will have from those particles and how much have been stopped and how much energy I have gained. Now this energy, this is the energy responsible about my physical dose, my biological dose, and my uh, weighted dose, clinical dose. But I can say, yes, you are right. The higher the stopping power, the lower dose I will have. No, the higher is the stopping power.
Does this stopping power relate directly to dose?
Mm, stopping power related to the linear energy transfer. Linear energy transfer is related to dose.
So indirectly related.
But the stopping power, it is
Effects.
I cannot say it's exactly LET, linear energy transfer, but it is kind of another way of expression, linear energy transfer. So stopping power, the higher is the stopping power, the higher is the LET.
What is the relation between LET and stopping power?
We will come next
I want to
next
Okay,
slide.
just like move to next.
Okay, but before I move
Maybe
next,
we can understand this after that.
I answer your question. What again? You say that for a physicist, you need to understand the difference between what is physical dose, what is biological dose, what is clinical dose, and what is weighted dose.
Yeah, like when we see some kind of graph, like a physicist may understand what is the mechanism happening there. Like I have idea about SOBP, but like a physical dose, but like here I am seeing the clear graph of physical dose, biological dose, or clinical dose, but I do not understand their
So the clinical dose is dose I use to treat patients, and it's acceptable clinically. I can use, and it depends on.
Also, why we check the physical dose?
I will tell you. Now it depends on what I am treating, how much dose I am sending, where I am sending. So, but this is my clinical dose. Oh, and then
I remember that the clinical dose for carbamide is like a sum up of this all these doses, like physical dose, biological dose, and
that's exactly what she's.
Newton. The data is from Newton.
That's what she said. Exactly right. Because for me, this is my next sentence. For me to have this clinical dose, I need to sum up both physical dose, or not sum up, I need to multiply both the physical dose and the biological dose. Now, what I get from this biological dose and physical dose is the clinical dose. Like this curve with this curve should give me this. Now, why those matters? Because the biological dose, it depends on something called RBE. My RBE with my physical dose can give me biological dose. When I have my biological dose, then I can determine if I can treat with patients depending on my RBE value. Does that make sense? Then if I'm good with my RBE value, I can make this biological dose plus my physical, or multiply by my physical dose to determine what is the clinical dose that I can use to treat this type of tumor. So one time, very quickly. Clinical dose is the dose we use to treat. This is what the patient take. Sometimes we call it the weighted biological dose, sometimes we call it clinical dose. That's what we use to treat the patient. Now for me, how can I get this one? I need to put in account my physical dose and my biological dose. My physical dose, it means the dose, the amount of energy I am sending and deposit this much of dose. My biological dose, it means the amount of this dose that can cause biological effect. Now when I am treating, I have to put in mind, I am treating a human being, or someone biologically is there. I don't just send dose to damage. There is some biological action and reaction is going to happen. This biological action and reaction, we can have a little understanding about it by something we call RBE. Because RBE tell me the relationship between radiation and the biological cell. Each cell have their own things. Yeah? So RBE and physical dose allow me to determine and understand my biological dose. Now, this biological dose I can estimate and determine my clinical dose to treat. Does that make sense? I go next. Okay, next. Linear energy transfer. LET. Now, LET is the average energy deposited by a charged particle per unit length as it travels through the matters. Spectrum of particles with different energy forming spread out Bragg peak. Therefore, at any point, there is a distribution of LET value from all individual plates. Okay, now, before I go deep into LET, because this is a topic I will never stop talking.
I want to learn
Yeah?
more about
So,
it.
I can tell you, LET in previously, and that we understand that stopping power, it is, I go back.
Imparted energy per unit
So
length.
stopping power, it is telling me, what is this? Stopping power is telling me that this material has the capability to stop this much energy coming from this number of particles with this thickness. So if I want to know the stopping power, I can take, for example, a part from here, and I can see how much energy this material has to absorb. So I can know it has the capability to absorb this much energy. This is stopping power.
To lose or to absorb.
This is the for the stopping power. It's the name is stopping power. So it is stopping the particles from stopping the particles power
Energy.
or
That
energy.
means that this particle lose power, lose.
Deposited all energy.
Now this energy deposited by the particle, we call it LET. You understand? Deposited by charged particle. This is LET. So if I want to know this energy, if I want, so this is the energy is the key things. Now, energy in this volume, I need this material, need this much of thickness to stop this amount of energy. Now I am calculating the stopping power. When I go, particles are depositing this energy in this volume. This is LET. So the equation of LET is the same one. If I take the minus out here, it's LET.
So it's just like LET is like a point, like a view from particle itself, like I'm
Yes,
particle,
yes.
I'm losing this
Yes.
this amount of energy
Yes.
within this length.
Yes.
And
You can
stopping
imagine it.
power is like I'm the material, I'm absorbing this energy,
You
amount of energy
can,
from this
you
particle,
can, that's,
right?
you can imagine it this way, yes.
And which is minus and is a positive and
You can
plus
say,
and minus.
well,
like
technically, you can, first, the way you're imagine it, you can do it this way, it's correct. The way, if you understand it by this imagination, is yes. That's first. But it is not 100% right.
Okay. What's the difference?
Different is the dependency of the stopping powers and dependency of the particle itself. Which what I'm trying to say is that there is some kind of situation where stopping power is not telling me LET.
Okay, so what is
It is just telling me the stopping power. You know what I mean? But leave this. You stick with the way you're thinking is correct. So because it's very famous way of understanding it is by saying this. Imagine you have a coin. You have a coin, and you have the two sides of the coin. One is, the other is LET. So this is LET. Now if I do this, this is LET. And you are right. Stopping power is like I am the material, or whatever example you say. You understand? So now LET itself is different. It has high LET, it has low LET. When the low LET interact, the way they lose, the way they do their ionization and excitation and this, you can see it is distributed along the volumes. Whereas, what did I do? Whereas the high LET, the ionization and excitation is happening like straight track. This is why we have a very good double standard break. Most of the most of the ionization and excitation and the interaction, the energy is going like a track line. Whereas in the low energy, the excitation and ionization is happening somewhere randomly. Now, so we go back to our figure, my biological dose or my RBE, my physical dose. What we want, what I want to emphasize here is that when the particle is traveling along the path, we understand the Bragg peak, yeah? Now, LET for each particle is fluctuating, is not constant. This one here. Why this fluctuation happening?
Energy distribution.
Why this fluctuation happening of LET? Because again, the Bragg peak I have is spread out, which means sum up superposition of many Bragg peaks. So there are many particles traveling. Those particles, each of them will deposit some kind of energy. When they are traveling along the path, when they deposit some kind of this energy along the path, they interact through excitation or ionization or sometimes little slowing down multiple Coulomb scattering or sometimes nuclear interaction. And all those together, they made the LET has different value along the path, fluctuating. Now this different LET value lead to different RBE value. The higher LET and RBE are always together. They move together. More LET, more RBE. Less LET, less RBE. Higher LET, higher RBE. They all together.
In treatment planning system, for particle therapy, we use like a LED guided optimization or something. But like in photon based, normally they maybe understand the dose volume histogram based on dose. So, but particle therapy we use mainly LED guided.
Now in photon therapies, LET is very low.
Yeah, they consider about dose.
They don't
They don't care about
they don't
IT.
yes,
They don't have.
it's very low.
Yeah. So
And why the LET is very low? Because in X-ray or conventional therapy, they use photons, and those photons interact to make electrons. By electrons, they use these electrons are the main reason to cause the damage of the DNA, so they can treat. However, these electrons carry very low LET with them. Us, we have high LET, which is way better. And difference between carbons and protons also in LET, because LET for carbon is higher, which means this is the biggest advantage of carbons out of all of them, because photons first is very low LET, second RBE is low too.
but like in particle radiotherapy, we use LED guided or RP guided.
Now for particle therapy, why we use this? Why we use LET guided? Because of RBE. For proton, RBE is 1, constant. Because LET is high, but is not as high as carbon. And in the
But I want to know it's
Huh?
true.
I think it's two RBE for photon.
Even if it's 2, still the main point is that RBE is not changing, not fluctuation. In us, RBE is changing. RBE is changing,
Is the LET dependent?
LET dependent.
What kind of is the behavior will that shape when we are designing treatment planning? I want to know like what kind of LED distribution we check when we are making treatment planning. I have no idea. That's an answer.
What do you mean is what type of I think your question is you did not.
Makes sense.
Yes, you like it does not.
Like
Try it once again.
Yeah, try again.
like LAT guided treatment planning. So mainly particular radiotherapy, we check the LAT behavior.
Now, the LAT behavior, it means this, for my understanding, how LAT are behaving along the path of Bragg Peak. So, this, how they fluctuating, different volume. So, what do you, when you want to treat, usually?
I never use, I have no idea about LAT, but I just know that as a physicist, they always check the LAT distribution to check the better outcome of
Yeah,
the
so
treatment plan.
the main reason why we want to have a very good LET is to make sure that we are causing the right damage, more double stand break, and we make sure our RBE is good. If we go more, I may kill the person. If I go less, I'm not gonna benefit from this amazing advantage of having LET. So the distribution of LAT is very important for us. How can we cause this damage? At the same time, because of this LAT distribution, sometimes certain volume can have the same physical dose, but not the same intensity of damaging, not the same intensity of LET. So maybe cannot cause the require to kill or damage the cell. So one more time, quickly and fast. LAT is very important for us.
Because many people in particular research, they are doing research about LAT.
For particle therapy, it's very important. Now, for photon therapy, LAT is there, but it's very low.
Don't consider it.
No, they do consider it. They do. It is the reason why they can damage DNA. It's very important too, but it is not as cool as for us. And particle therapy in general is cool because of this LAT. Photon therapy's RBE is constant. Now, for particle therapies, we have the heavy ions and we have proton. Proton have high LAT, not as high as our LAT, particle therapy, heavy ions LAT, but consider high LAT. RBE of protons is also constant. RBE for heavy ions, no, depends on LAT distribution and LAT's behavior. Now, if you go to the Bragg peak,
I think for proton and heavy ion, carbon ion, both same.
no, RBE for carbon ion is
And
not.
proton.
No.
Proton.
No, we are way better. Proton and photon RBE is slightly the same. One of them is 1 and the other is 1.2. Or one of them is.
RB for carbon is higher than photon than the photon. But considering this RB is from in vitro experiment. It's not same with exactly same with the clinical data. So when we treat patient, situation changes and RBE is different. So we presume this RBE in clinical treatment is not that high as we can see from the experiment. So it's not 3, like 2 or something.
Also, to emphasize her saying in this graph here, RBE depend in LET and the type of cell.
The first one is the cancer cell.
Some cells respond.
Red one.
Some cells respond better than other cells. First one, for example, this type of cancer cell has this respond to LET with RBE. Do you understand? This cancer cell will have this type of response. So RBE concept is not yet fully understood. However, we have a very good way of knowing it. You understand? Now, there are three different types of cells.
So first one is cancer, the red one. And the green one, CHO, is Chinese hamster ovary. Okay. And the third one, I don't know. Let me check. You can continue.
Okay, so I have LET here, yeah? And I have RBE.
What is the ideal graph for like LET and RBE? Like here, we see at first low, then high.
The whole thing is to illustrate that RBE, it's changing with LET. The more if LET increase, RBE will increase, but also it depends on the type of cells too. Every cell has different way to respond. You understand? For example, the cancer cell here respond by this way, the V79, where RBE increase and suddenly decrease. The Chinese hamster cell has this way, RBE is increasing. The response of the cancer cell is better, is higher. However, it is different. Each cell has different way to respond to LET. And then finally, to finalize and finish, we come up with this, and not we come up, the world, the scientists, researchers, they come up with this relationship where when charged particles slowing down, they will deposit low dose, which mean higher stopping power, as you said before. Higher stopping power, which mean
higher
LET, which mean higher dose average LET, which mean higher RBE. When the charged particle is going fast, will deposit higher dose, which mean lower stopping power, which mean lower LET, which mean lower dose average LET, which mean lower RBE. I go next. Now, I think this is the last slide, yeah? Or the one before the last slide. Fragmentation. So, the whole time, the whole thing when we were talking about Bragg peak from here all the way to falling down. In proton therapies, they don't have fragmentation tail. In photon, they have slightly secondary particle, but not fragmentation. Now, in carbon, or heavy ions in general, we always have this fragmentation tail. Why? So we have this fragmentation tail is the many LET of the secondary particles and break up nuclei along the path. So when the charged particle enters along the path, secondary particles will appear. LET is fluctuating, is slowing down, losing a lot of energy, losing its energy. Now, it is heavy. It has heavier mass. When it is moving, it loses its mass, and this mass can produce secondary particles. When it hits the target, the projectile here, it hits some kind of target. There is two ways of happening. It's either will like hot and fragment into highly nuclear, and then it will produce secondary particles because it is heavy and hitting the whole time. So it will keep moving, but some particles will be produced with an energy, with an LET, let's say, it's more correct. This lighter fragments travel very long path, so they will make it further than the treatment region. So because they are lighter, they can travel further, so they will pass through the desired area with some kind of LET. And those many secondary particles, because of the nuclear interaction along the path or the fragmentations happening, will create high energy LET. Now, one of them, not necessarily high energy, but many of them, they become high energy LET. They produce the fragments here with different value of LETs. When this hit the target, it break up to smaller fragments sometimes, and then shattered and produce the secondary particles. Those secondary particles with high LET are unwanted. They can increase risk of secondary cancer or another cancer. However, this fragmentation tail, it's the main disadvantage of using heavy ion therapy.
Proton don't have.
Proton don't have, that's true, but we have heavy ions. So multiple the scattering happening here in along the path is very weak. Proton, they have too much scattering happening along the path, and this too much scattering happening along the path also produce more secondary particles. But the secondary particles proton is producing, it's inside the field of treatment. We are outside the field of treatment. And so even proton has disadvantages in this scattering here. We don't have scattering here. We are very heavy. But carbon does not have scattering along the path. It's very heavy. It scatters slightly, slowly. However, even the main disadvantages is this tail, but in general, particle therapy is very good in targeting, very accurate. So this tail, we can somehow not avoid, but manipulate, manage. We can shift it slightly, but we cannot avoid it, but we can manage it. Or manipulate it, let's say.
Collimator and the range factor.
No, it's not enough to for example, in an ideal situation, we don't want this fragmentation thing, but we have to deal with it. So it's there. We cannot avoid it. We have heavy particles. It will have their multiple Coulomb scattering, the excitations, the ionization, the nuclear interactions. They will fragment.
Like tumors out of field, secondary.
Usually they are out of field.
Yeah. So if they're out of field, if we use the collimator, saying that our target, 3D target, like yeah.
No, but
Why we can't approve?
I understand what do you want to say, but we want to shift the whole brag a little bit a little bit closer to make it closer, but the same times you don't want to play with this because this is what make you treat. This is the area where tumor is here. If I want to put tumor here, and I will put collimators and shift it a little bit closer, so my tumor is going to be here. So this area is going to be shift closer too. Does that make sense?
So what do we use well this actual clinical treatment?
We deal with it.
Yeah.
We deal with it.
What?
We keep it. It's there. It's not. We treat. Secondary particles will happen, but it's not.
We just leave it, or
No.
We explore.
No. We don't. We make sure that when we are delivering,
we are focused on treating the cancer.
No. Yeah. But we will make sure when we are treating, we are delivering this amount of fragmentation.
The treatment for of cancer is a priority. And,
yes, but also we don't ignore it. We are paying attention that the amount of dose we are sending is still very safe. That this fragmentation tail will not cause problems.
Okay.
So we are putting this into account as well. And nowadays, for example, the research I am doing is I am also trying to use this to take an advantage of this type of LET distribution along the area. So I can manipulate the distribution of LET to make it more inside the cancer. But we don't just, it is unwanted, we don't, but it's not, we ignore it.
There's no specific part or tool or some like collimator or something.
For now, no.
This.
For now, no. Until now, this is existing. This is the main. Now it is main disadvantages. It does not necessarily mean it is so bad.
Maybe secondary fragmentation creates the deterministic effect, like after 10 years or 12 years make the problem, so doctors may become like for older patient they doesn't consider
follow up.
right now cancer rate is more important.
First,
Actually, consider many factors in the design.
the benefits of using carbon ions
Because
or
for
heavy
cancer
ions.
treatment, we always don't use the radiation therapy. Sometimes we go through chemotherapy or immunotherapy.
Yeah.
Many things maybe they consider about the age, the treatment. So many factors.
The benefit of carbon ions outrage this little disadvantages of the fragmentation tail. And although the disadvantages of fragmentation tails is there, we still have many different way to not make it very dangerous. First, we know carbon ions is very accurate. We know how far things will travel. We know that this our high LET can cause double standard break here easily. We know that we are capable of sending sharp dose localizations because of our Bragg beak. Me, for example, in my research, for the last point, the clinical use, I do use carbon ions to try to solve for pancreatic cancer. When pancreatic cancer is very complicated because first is hypoxic, radio resisting, will resist conventional radiotherapy, and proton will not give enough LET to cause the damage wanted. Carbon ion is very promising. Organ at risk around the pancreas is very close. Spinal cord, very sensitive to radiation too, and very close. Spinal cord, for example, stomach, there is a gap and there is an air in the intestines, will cause another fluctuation. Proton will easily fluctuate. It's not as heavy as carbon. Carbon is heavier. It will fluctuate too along the path, but not as much as photon or proton. So those are advantages, and there are many, many advantages of carbon. Outtake this little disadvantages of the fragmentation tail. Now, I am not saying fragmentation tail is good. I'm saying it's a little disadvantage. We still can put it under consideration. We still can treat with it. And yes, maybe if we send too much high LET coming from the fragmentation tail to the unwanted area beyond the target, maybe after 10, 15, 20, 30 years will lead to secondary cancer. However, when we treat, we are also considering at the same time to take an advantages of carbon ion therapy with less fragmentation tail. So we don't increase the probability of developing higher secondary cancer in the upcoming years for the patient. And with this, I come to an end. This is conclusion. Now maybe we know some part of physics, but knowing is different than understanding. And to understand physics, we need to understand this kind of things, which I do understand. I don't know about you. And I put this kind of things to conclude. Now, my conclusion, can you understand it from there? My conclusion is simple. One, particle therapy interact with matter different than photon therapy. They go through excitation, ionization, multiple column scattering, and nuclear interactions. Now this ionization, excitation, lead me to something we call it the stopping power. For me to have this stopping power equations, I have to go through a lot of Coulomb force equations, and then we angular momentums, and then the conservation of energy, where the mass and the energy are the same with many different equations. Very complicated and a smart way of doing it, beautiful way of doing it.
We use the simplest one, but
All this is happening to come to this one. And this is not all, this is just ahead of many of all things. But many calculations, like 5-6 pages of a beautiful physics or calculation and math to come up with this equation. Now this tell me the stopping power tell me how I can understand my LET, which has lower and higher LET. This amazing lower and higher LET, particularly the higher LET, it's what we use to treat tumor safely, putting in our mind our physical dose and RBE. So to conclude, particle therapies, it is the best. So far, heavy ions are the most accurate, the most advanced. It is not like photon. Interaction is happening through excitation and ionization and nuclear interaction. Stopping power and LET are very important concept to understand if we want to develop ourselves in particle therapy, and it is more accurate and more safe than others. Thank you very much. Arigatou gozaimasu.
Can you show me the RBE figure before we discuss? This one. Yeah. Thank you.
Finished? Oh, this is 2-hour lecture.